And of course also thank them for inviting us and giving us this chance to talk about sort of what we like, yeah, discrete differential geometry. Anything else?
It's meant to be introductory, but it probably isn't.
Oh yeah, so we're trying to do a real lecture, yeah, which means, trying to introduce the topic really. Yeah, I want to use this one, Helios. And so also that means for this to be a lecture, you should ask questions, yeah, at any time, not at the end. When you have a question, ask it right then. This question can be, please show me the last slide again. Yeah, that probably means many other people also want to see the last slide again. It can be, I don't understand this, that, or any questions. Yeah, and we are happy to have more discussions than just presentation. And we have buffers that we can leave out in the end. So yeah, okay. Thank you.
Yeah, okay. So we are going to do DDG, so discrete differential geometry for geometry processing. And like my part can be maybe roughly described as parameterized surfaces. Yeah. Well, what is discrete differential geometry? Well, it's difficult to describe in one slide, but for today, let's think about it like this. In smooth classical differential geometry, you would deal with surfaces and curves on these surfaces. And then in discrete differential geometry, we deal with polyhedral surfaces, so meshes and polylines. And the goal of discrete differential geometry is to develop a geometric theory, an independent theory that is based on these discrete objects. And yeah, why should we care about that? Personally, I care about it because I think it's a very beautiful mathematical theory. But today we want to convince you that it can also be very useful. For example, if your discrete formulation, if your theory is already based on meshes, then this is very easily turned into computer code. Or say if you are looking for meshes with certain features that are like geometrically pleasing or have good structural properties, then it can be very useful to understand how these meshes relate to curves in differential geometry. And one last part that we are going to talk about today is how imposing restrictions on meshes can also help you to not only find meshes with certain features, but also surfaces, so entire shapes with certain features. Yeah, this is by far not everything. I will only talk about quad meshes today, you will see, but you could also do discrete differential geometry for triangular meshes, and there's much more, but this is roughly what I'm going to tell you now. To be a bit more concrete, at first, we are going to look at meshes and we want to optimize them to have like planar faces and then also orthogonal faces, yeah, as mesh features. And something that is always theoretically but also practically interesting is if our mesh features are invariant. Invariant meaning they are preserved under certain transformations. And here we will meet these circular meshes and then these conical meshes. And another, for us, interesting mesh feature can be a relation to offset structures. So say you want a mesh with planar faces, and then you offset it along the normal direction, and the offset mesh should still have planar faces. But usually when it comes to structural engineering, you also want these beams in between defined by the normals to be also planar. So we are not only interested in features of the mesh, but also of the discrete vertex normals. And then eventually we're gonna look how mesh features can be used to obtain developable surfaces and minimal surfaces. So here you see some minimal surfaces. And the methods, the tools that we are using is mainly going to be optimization. Optimization combined with this knowledge of smooth curves, or how our discrete objectives relate to smooth curves. And then we're going to play a bit around with transformations and subdivisions, how they can be used as a design tool. Okay. First, problem setting. Imagine you are confronted by an architect, you as a geometry processor, and this architect has a shape designed, and now the shape is supposed to be built in a real architectural building. And so you are tasked with the challenge to quad remesh this shape with planar faces, because if you want to build it with glass panels, then these glass panels should be planar, otherwise it's going to be super expensive to build. So how can we find the right quads on this shape? So one thing is easy, we can optimize the quads to be planar. So this is basically going to be our pattern. We introduce some energies and then we minimize these energies. And here this energy is supposed to measure planarity. We can introduce a normal vector as auxiliary variable in every face, this NF, and then we want this NF to be orthogonal to all the edges. So this scalar product NF times the edge vector should be 0. We square all of them and add all of them. And then we also require NF to have unit length so that it doesn't shrink to 0. And then we have our energy term. And you can minimize this with any gradient descent method. And if this energy term is 0, then all the quads are planar. One very essential side note: whenever we do this local mesh optimization, it is important to add a fairness term that prevents the polylines in the mesh to become super zigzaggy. So to keep everything good looking, more or less. Typically, this is a term like this that forces every vertex to be the midpoint of its left and right neighbor, like along every polyline. If this energy term would be 0, then all the polylines would be equally spaced straight lines. So we don't want this to be really 0, 0. This is just there to guide the optimization. So we always add this term with weight that is typically small in comparison to the planarity energy. And when you iterate the optimization, typically in the last iterations you can set this weight to 0. Okay, if you remember the very nice talk about convex optimization problems that we heard yesterday, you maybe remember that in these optimization problems, sometimes the challenge is the initialization. And this is the case here as well. So how do we initialize our quad mesh? And here, discrete differential geometry comes to help, because we know that a planar quad mesh is the discrete version of a conjugate net of curves. So we know which smooth curves to look for in our shape, and then we can just sample them and start our optimization from there. What are conjugate curves? Who knows what a conjugate curve is? Who has heard this before? Yeah, okay, some people, nice. Okay, conjugate curves can be defined like this. Suppose you have two families of curves on your surface. So they cover the entire surface. Think of it as like the family of blue curves and the family of red curves. And then you can do the following. You take one of those red curves, and in every point, you take the tangent of the blue curve crossing the red curve. So you get tangents along your red curve, and they form a ruled surface of straight lines. And if this ruled surface is a developable surface, and this works for any curve, then your network of curves is conjugate. Maybe, okay, what is a developable surface? Huh? So you can understand it like this. In a developable surface, these rulings, infinitesimal neighbors of these rulings intersect. So again, here this means infinitesimal neighboring blue tangents with this neighboring along the red curve, they intersect. And if you delete the word infinitesimal here, this is actually the property that we want in our quad mesh. Because if you extend the edges, you want neighboring edges to intersect if they are in the same plane. So this is actually the property that we want in our mesh, and this is the smooth version of that. How could we compute conjugate curves? So let's do a bit of math. Suppose we have a local parametrization of our surface, and we denote the derivatives, the partial derivatives by fu and fv, and then we can define the so-called fundamental forms. So some matrices, first fundamental form and second fundamental form, and then you can characterize conjugate directions by the fact that they are orthogonal to each other with respect to the second fundamental form. Okay, so this is just something you can compute, where here A and B are the vectors in the parameter domain. So for any given direction, you can find the corresponding conjugate direction. Now, this means if you're looking for conjugate curves, you could do the following. You start with any set of curves covering your surface, and then in every point, you take one direction, you compute the corresponding conjugate direction, and you get a vector field, and you integrate these vector fields to get the second family of curves. And then you have your conjugate family, right? However, things can go wrong. There's something you have to be careful. If your curves that you chose first are self-conjugate, so if they are too close to the so-called asymptotic curves, then your curves will be self-conjugate, and quads can become very acute. So there are some directions in your surface that you want to avoid if you want to have a nice looking quad mesh on your surface. And the best way to do this is to choose the first family in a good way, and namely use principal directions or principal curvature lines. Principal curvature lines, they have been mentioned in the first talk that we heard on the graduate school. What are principal curvature lines? I'm gonna try to motivate it quickly. Let's start with a planar curve. You know, the curvature of a planar curve in a point P can be defined as 1 over the radius of the osculating circle. The osculating circle being the circle that best approximates the curve at this point. So you get it if you take 3 points on your curve, you take the circle through 3 points, and then you just move the 3 points together to 1 point, and in this limit process, you get the osculating circle, just like you would obtain a tangent in a limit process. So this is the curvature of a planar curve. By the way, this also works for a space curve. You can also do an osculating circle, and then the plane that contains the osculating circle is the osculating plane. This might be, I might mention this again a bit later in this presentation. Now, with this picture in mind, we turn to a surface. In our surface, we have a point P, we have a tangent plane on P, and we have a normal vector. And we take a plane through P containing this normal vector. And this plane now cuts a planar curve in our surface. and we compute the curvature or the osculating circle, yeah, at this point P that we get by intersecting this plane with the surface. And we can now rotate our plane around this normal vector by varying alpha, and we get many different curves. Every curve has a different osculating circle. And there will be one circle that is the biggest circle and one that is the smallest circle, which gives us the maximum curvature and minimum curvature of the surface. And the directions that correspond to this maximal curvature and minimal curvature, these are the principal directions. Integrating them gives us the principal curvature lines. And they have many really cool properties. First, these principal curvature lines are always orthogonal. So the direction of the surface in which it maximally bends and minimally bends, they are always orthogonal. And they're also conjugate. So this is, if you're interested in not acute planar faces, this is the best initialization for your optimization algorithm. Also, the reverse is true. Any net of curves on your surface that is conjugate and orthogonal already is the net of principal curvature lines. So you can reverse this to find principal curvature lines. They are the eigenvectors of the so-called shape operator. This can also be useful to find principal curvature directions if you have a smooth representation of your surface. And the normals along a principal curvature line also form a developable surface. This will be, I will mention this a bit later again. What can we do with this now? First, second fundamental form, first fundamental form. Together, they define the shape operator. It's just a 2x2 matrix. We can compute the eigenvectors of this matrix, and this gives us the direction of the principal curvature lines. So this is a way to compute them. So if you're given a smooth shape or like a fine triangulated mesh, and you want to remesh it with a quad mesh, you can do it in the following way. First, you compute the curves, the principal curvature lines, and then you remesh along these principal curvature lines. And here you see it is already quite good, and then you can have your optimization run to planarize even further. And this is sort of a suggested pipeline to solve this planar quad remeshing problem. Okay. Our principal curves, however, they can do a bit more. They have many features, I said, and I want to briefly talk about this last one that maybe seems a bit weird because, yeah, I'm talking again about developable surfaces. This means the following. If you have your surface and then you have a curve on your surface, then you can trace the normals along the surface. And this defines a new surface now. And exactly for principal curvature lines, this is again a developable surface, meaning neighboring normals intersect. So think of it as these neighboring edges, if you extend them, they intersect. And this is a useful property on the discrete level for these offset structures that I mentioned in the beginning. Yeah, usually when for example in architectural applications, but also other stuff. Yeah, you're not only like two-dimensional anymore. You have a top and a bottom layer, and you want both layers to be planar, but then the beams connecting them should also be planar. But this is exactly meaning that, these strips are developable surfaces. The normals lie in the same plane. This is exactly something that we can get if we used a principal curvature parametrization of our surface. And it can also be realized or observed at a discrete level. And it is probably best captured by these two discrete versions of principal curvature lines, circular meshes or conical meshes. They're not too intuitive, maybe, if you want to understand why these exactly are the discretizations or so famous discretizations of principal curvature lines. Then the point of view of higher geometry that Niklas will represent later is very useful. So anyway, what are these meshes? So the circular meshes, they can be defined by the fact that every face has a circumcircle. All four vertices lie on a circle. And they have nice properties. They are invariant under Möbius transformations. These are transformations that preserve conformality, that preserve circles. And this invariance can be a design tool as well. Then we have features like the sum of opposite angles in every quad is equal. This is also a characterizing feature, and we will later use this in an optimization. And they allow parallel offset structure at constant vertex distance. So if you want your mesh and you want to offset it with a parallel mesh, and you want that all the vertices have equal distance throughout the mesh, then it is possible with a circular mesh, and it's also only possible with a circular mesh. So this is also a defining property of circular meshes. We can obtain them through optimization again, and for example, the angle property can be used. Optimizing the angles to have this, this property that the sum of opposite angles in every quad is equal or is equal to pi, makes every quad a circular quad. Conical meshes have a very similar flavor. Yeah. Yeah, very good question. Okay. So there is as a certain degree of freedom in the normal. You can choose your first normal in the first vertex, and then you reflect it on the bisecting plane of every edge to get the next normal. So you start on this vertex, and then there's on this edge, there's a bisecting plane, you reflect it. And you reflect again, and you can reflect again, and this will give you the same normal as the one with which you started. Only working again for circular meshes, but in circular meshes this works. So you can start with one normal, iterate over the entire mesh, and you get your normals with the desired property. Or you do an optimization procedure because you know it works for circular meshes, and then you just can require the coplanarity of normals. Sometimes a better controlled process is if you have a very large mesh, you don't really want to start with one vertex in one corner and reflecting it all over the mesh. Yeah, but it is not uniquely defined. Okay. Yeah. Conical meshes have a very similar flavor. They are defined by the fact that in every vertex star, the four faces touch a common cone. Or you could also say the normals of the four faces lie on a circle. The face normals. And these meshes are invariant under Laguerre transformations if you apply the Laguerre transformations to the planes containing the quad faces. And there's also an angle characterization. Now the sum of opposite angles in every vertex star is equal. And these conical meshes allow an offset structure with the property that now the phase distance is constant throughout the entire mesh. And again, this is a defining property. And the normals that you use here are just the cone axis. Here it's a bit easier. Okay. Yes, exactly. Yeah, you can just use this cone axis as the vertex normal. Yeah. Okay. Again, we can formulate it with a angular optimization term, and now we could, for example, combine these ideas of principal curvature discretizations with a subdivision algorithm. So you can do the following. You start with a very coarse geometry with a few quad faces, and then you optimize this to, for example, be circular. And so you know that roughly they follow principal curvature lines, and then you subdivide, you get something finer. Subdivision means, yeah, you split up every face to be 4 faces. And then you optimize again, subdivide again, you alternate between subdivision and optimization until you are happy with the result. And this is a very controlled process. And the other tool that you could use is transformations. So here you could, for example, you could start with one geometry that you already understand very well, that you know very well. For example, here the n-upper surface, where we just know the family of principal curves, and so we know which curves to trace, and we know the normals and everything. And because the principal curvature lines are preserved under Möbius transformation, for example, we can apply this Möbius transformation, and we get a new mesh that still has all the nice features that we need, and then we use this to turn it into a architectural structure. For example, here is the origami architectural structure where we need all the normals and, yeah, make use of this offset structure. Okay, so this was the part about principal curvature lines and planar faces. And now we're going to drop the planarity condition and see what else we can do with curves, with meshes. So I'm going to talk a bit about discrete orthogonality now, how we can define a mesh to be orthogonal. And then we combine this with geodesic nets, discrete geodesics, to obtain developable surfaces, and then with asymptotic curves to obtain minimal surfaces. Okay. What is a good definition of discrete orthogonality? Requiring that every angle is 90 degrees in the mesh is not too sophisticated. This would limit the degree of freedom of the mesh too much. So we're looking for something else. And one approach that is actually very powerful, I believe, is the approach of binets, first introduced by Popenko, Schiff, Suris, and Techter in 2018. And a binet, basically the idea is you use 2 meshes at the same time to discretize the same surface. And then you can say that like the first order properties, they are encoded by the corresponding edges. So those 2 meshes, they are combinatorially dual. For every face of one mesh, you have a vertex of the other, and vice versa. And for every edge, you have a dual edge of the other mesh. And all these first order properties that are related to first derivatives, you can encode them in these corresponding dual edges. So if you want your parametrization to be orthogonal, you just say, okay, I want here corresponding dual edges to be orthogonal. They don't need to intersect, but the directions can still be orthogonal. Or you could say you want a rhombic parametrization, which we will use later, then dual edges have the same length. And there are actually many more things you can do with them. I believe this is a very powerful approach because it has turned out that it generalizes a lot of the existing discretizations, actually, that were used in discrete differential geometry. So a lot of them already turned up in pairs. So, for example, this here is actually a combination of a circular mesh and a conical mesh. They always come in pairs. If you have a conical mesh, you can always compute the corresponding circular mesh and vice versa. And this is also true in other cases. For example, here you have Koenig's meshes, and their discretization also comes in pairs, and together they form a Koenig's binet. So I don't want to talk about this too long, but if you're interested, I want to encourage you to check them out. It is quite still a bit new, but I believe there's a lot of potential. However, I do acknowledge the fact that some people refuse to use it because it's too many meshes. You just want to deal with one mesh and you don't want to do everything that you did again just for a second mesh. So compromise could be the following. Another orthogonalization idea based a bit on binets, but then forgetting about binets again. The idea is the following. These binets naturally arise as diagonal meshes. So if you take this white mesh and you trace the diagonals of this mesh, this gives you actually a mesh pairing of two different meshes. And this also works in the smooth setting. If we have a parametrization, we can switch to the diagonal parametrization, by just switching from uv to u plus v and u minus v. And then we know that this diagonal parametrization is rhombic if and only if the initial parametrization is orthogonal. So we can do the following trick. We say, okay, our initial mesh, so now this white mesh, is orthogonal if the corresponding binet defined via its diagonals is rhombic. And basically this boils down to saying, okay, in every quad, we want the diagonals to be of equal length. And personally, I like this definition because you can also observe it in the medial lines. So in the lines connecting opposite edge midpoints, they intersect orthogonally if and only if the diagonals in the quad have equal length, which is quite neat, I think. And this also has good approximation order of orthogonality, and it doesn't depend on any quad being planar. And this is a contrast to the circular or conical meshes that only work for planar quad meshes. And we want to apply this notion of orthogonality now to obtain developable surfaces. I mentioned developable surfaces before. If you heard the name developable surface, most probably you heard it in the connection that they are those surfaces that can be folded from a flat sheet of paper. I was thinking, yeah, I have to take a paper with me when I go to my talk, and now I still forgot. But yeah. Another characterization, the most famous characterization of developable surfaces is you can bend them isometrically from planar sheets, which makes them very interesting for anything that you really want to manufacture. And here is one of these examples by the Walt Disney Concert Hall by Frank O'Gary. You maybe recognize the style. Yeah, he is the same architect of this, the Guggenheim Museum. I took this photo yesterday, and I thought, now I have a good example of a developable architectural construction. However, I'm not 100% sure if it really is developable. I was looking a bit on it. I was doing some research. My boss thinks it is. ChatGPT thinks it isn't. Difficult situation. Yeah. I was looking a bit before the reflections of the sunlight. I guess it's not developable. But the concert hall definitely is. And maybe they had more budget here, so they didn't need to do it developable as well. So how do we obtain our developable surfaces? We're going to use this idea that we use, or we want to find a orthogonal geodesic net. This is an idea that has been used by Rabinovich, Hoffman, and Sokine-Hornung in a series of very nice papers. And we already have orthogonality. We just need to know what geodesics are and how we discretize them. They have already been mentioned a few times. Geodesics are the shortest path between 2 points in a surface. And you could also characterize them by this, their osculating plane, the plane in which their curvature circle lies, so in which they curve. The osculating plane of a geodesic is orthogonal to the tangent plane. It's orthogonal to the surface. Yeah. So you have here this vector. Yeah. This one vector is the normal of the surface, and the other vector is the normal of the curve. Yeah. Going orthogonal to the osculating circle. And in the geodesic, these two circles coincide. So all the curvature of the geodesic happens in a plane orthogonal to the surface. So from the point of view of the surface, the geodesic doesn't curve. Yeah, you could say the surface only sees what's happening in the tangent plane. And if you have this notion in mind of a geodesic, and you do a bit of okay, yeah, you get to a discrete notion of geodesics that will show up a bit later. Anyway, we can use this for developable surfaces because orthogonal geodesics only exist or can only exist on developable surfaces. And the reason for this is the famous Gauss-Bonnet theorem. If you integrate the Gaussian curvature K over some area Q, and then you add the geodesic curvature integrated over the boundary of this domain, then this is equal to 2 pi minus the sum of these exterior angles. Okay, so this is a formula that holds, and if this boundary happens to be geodesic curves, yeah, then this geodesic curvature, this is the curvature of a curve that happens in the tangent plane, and this is 0 for geodesics. So then this term is 0. And if all these curves are orthogonal, then all these exterior angles are pi over 2. So this term is 2 pi, so the right side is also 0, meaning that the integral over the Gaussian curvature over any part of the surface is 0. So the Gaussian curvature is 0, which is another characterization of developable surfaces. Okay, with this idea in mind, we know we just have to look for a net of discrete orthogonal geodesics. We have an energy term for orthogonality, just giving us diagonals of equal length. And we combine it with an energy term giving us geodesics. And okay, you have to do a bit of a computation from what I said before to see why this is a good discretization of geodesics, but we arrive at the fact that opposite angles in every vertex star are equal. Okay, this is a common discretization of geodesics, and combining this and optimizing this total energy gives you surfaces that have close to a 0 Gaussian curvature, so something close to developable surfaces. And this is a game that you can play with few combination of curves. Yeah, there are many surfaces that, or set of curves that can have special properties only on special surfaces. Another example would be minimal surfaces and the asymptotic curves on minimal surfaces. So we're now looking at orthogonal asymptotic curves. Briefly, what is an asymptotic curve? You have an osculating plane, yeah, the plane in which the osculating circle lies, in which the curve curves, yeah. And if this osculating plane coincides with the tangent plane at every point, then the curve is an asymptotic curve. Okay, and orthogonal curves, orthogonal asymptotic curves can only exist on minimal surfaces being the surfaces that locally minimize the area. And this is due to the fact that this angle, yeah, between asymptotic curves, between two asymptotic curves, is related to the quotient of the principal curvature values. If you don't know what they are, then yeah, just forget about this. But the minimal surfaces are characterized by their mean curvature being 0, the mean curvature being the mean of these principal curvature values. Yeah. They are the, actually I mentioned them before. You remember the osculating circle? The osculating circle of the principal curvature lines, 1 over the radius is the principal curvature values, kappa 1 and kappa 2. And if their sum is 0, then you have a minimal surface. Okay. And now we just need to know what asymptotics is, and this fact that the osculating plane is the tangent plane translates to the discrete setting with every vertex star being planar. So this vertex and all its neighbors lying in the same plane, and this is easily formulated in an energy term. We just want n to be orthogonal to all these edge vectors. Again, we normalize n, and minimizing this, yeah, gives us these minimal surfaces. And in fact, we even get a bit more than just minimal surfaces, because we get already this asymptotic net, which could, for example, be useful because this grid shell has the property that all these beams, because they are asymptotic, they can be developed into straight lines. So they can be deformed, yeah, and into straight lines, because the normals, if you look at the surface defined by the normals along an asymptotic curve, then in the point of view of this surface, the asymptotic curve is a geodesic curve. So it's straight if you flatten it to the plane. Anyway, with this, I want to conclude the first part of our talk. Yeah, so thank you for your attention, and I hand over to Niklas.
Yeah. Okay, guys. Oh. Take questions.
Sorry. Yeah, maybe first some questions, and then we can maybe have a short break, and then we continue. Okay. Sorry. Yes. So mm-hmm. Yes, yes. So I basically I agree. Yeah, this should be a way to compute principal curvature direction. So if you have your mesh and you have a good notion of, okay, this is orthogonal and this is planar, then you should be able to tell the principal curvature lines from this mesh. I assume the tricky part is going to be the combinatorial singularities of the mesh, because they can occur in those points where, in those umbilical points, yeah, where the two principal curvature lines or the principal curvature values are the same, and like locally the surface looks like a sphere, and there you can have combinatorial singularities. So you would somehow need to respect this in your approach. Okay, yeah, yes, please. Yeah, good question. So you mean you have this piecewise smooth, but with a crease in between? Yeah, and you still want to have a good offset structure. So basically, if you have something like let's say a conical mesh, yeah, which is what we used most for offset structures, then at the boundary there is an additional degree of freedom, because what you want all the faces around a vertex touching a cone. If they're just two faces, this is easier. So like all the inner vertices, they have a unique normal, but the vertices on the boundary, they do not have a unique normal. And this freedom can be used to match normals for different patches of conical meshes, for example. It is possible that there are some topological constructions where something goes wrong. So yeah, I would say in general, this is a problem that you can deal with, but yeah, it can become also tricky and like if you have something where more than 4 patches meet in a vertex, for example, then this vertex will be also problematic using the conical approach. Yeah, so things can go wrong, but in general, it's solvable, I would assume. Yes? Ooh, this is, I'm on camera. So, okay, no. Quad meshes have very nice properties. And one reason to use them in, let's say, architectural stuff is that you can have torsion-free nodes. Yeah. So this beam structure, yeah, when you have like, you want a straight beam where 4 beams meet in a straight line, this is only possible if you have a quad mesh. This is not possible anymore in a triangular mesh. Then your triangular mesh is already automatically a sphere. So this is a big advantage, but I'm not an engineer, I cannot really tell you if it outweighs the big advantage that not automatically every face is planar, because this is also very useful. So I would say you can get more interesting designs only from this design perspective by quad meshes, but the triangular meshes are a bit easier to use. I personally do most of my theory with quad meshes because it fits easier in this approach that I take a lot of times relating discrete differential geometry to differential geometry. But I would never dare to say that they are like in general better than triangular meshes. This would be too much of a statement. Yeah, okay. Yes, very good question. So usually it's not the optimization is not a big deal and it's not a problem because we invest the time to have this good initial guess. And then we don't care about the convexity that much anymore. But it comes at the cost of thinking a lot about how to start the optimization. And other approaches are also like possible, and there are also some where you think more carefully about the energy also from a numerical perspective, and then you just have automated pipeline and you just optimize. Yeah, very good question. Okay, then thank you very much, and let's make a short break and continue afterwards.
Guys, sorry, break's over. Time's short. All right, very good. So, I'm already a bit tired. I guess you are too. I'm gonna try to finish sort of on time. Okay, we just now had a very nice talk. Now there's gonna be the second part, probably not as nice. And okay, all right, I start with bad news. It's sort of a math talk. I mostly do pure math, but I've been surrounded sort of all my academic life by applied mathematicians. I'm in the applied geometry group in Vienna. So I'm gonna try to keep this simple, and primarily I'm gonna try to advertise, to use a tiny bit of pure math in applications in geometry processing. Okay, and again, please ask questions if you have any. Okay, what's the plan? I have to explain what higher geometry is. I'm gonna try to explain why you should use or could use higher geometry. Then I'm gonna focus on one example. The most popular example is Möbius geometry, an example of higher geometry. And then it's gonna be a bit more of a crash course and maybe a bit of a more like walking through the zoo for a bit more higher geometries. And then finally, I'm going to show you literature in case you are actually interested. Then you can read up on details there. Yeah. Okay, what is higher geometry? It's a good question, but first we need to figure out what is geometry actually. So I work with all sorts of people, and that means this question has all sorts of answers. Right? Really, some people think graph theory in the plane is geometry and so on. So I'm just going to give you a definition for this talk, and for this talk you'll have to agree with me. Afterwards you can go back to your own definition. So what is geometry? For me it's, I have to have some space of objects, could just be points. And then I need to have a group of transformations, usually called symmetries, and that is for me geometry. And well, how do we know it? I think everyone, I hope, knows Euclidean geometry. So in this case, we sort of, we live in it, can be debated, but it's our intuition of space. Yeah, we have three-dimensional space, there's lots of points in there. And then I have transformations that preserve, lengths, for example. So isometries, which are, in the top you see just a translation, then you see a reflection about the line, and you see a rotation. These are the typical Euclidean transformations. But there are other examples. Another example you're probably all familiar with is just linear algebra. In this case, the set of objects is just vectors. And the transformations we use are just linear transformations, so matrices. And the third one I think that everyone is sort of comfortable with is affine geometry. And we sort of just combine. Now we have translations and linear transformations. All right, and sort of these are the standard examples, I would say. So now, how do we get to higher geometries? That's not really a clearly defined name, but again, for today, the idea is we start with Euclidean geometry. We like it, we use it, but then we change it a bit. For example, we could allow more symmetries. So in the top right, you see, again, the same blue triangle, but now I'm somehow able to reflect about a circle. And I'll explain a bit more detail later what that is. And that means where there's more transformations, more symmetries, and then things change. And yeah, okay, I'll talk more about this later. But I could also just sort of change what my space of objects is. Yeah, instead of just looking at points, I could treat points and circles in the same fashion. And we'll see an example of this as well. Or, of course, I could combine. Yeah, and then have more general objects, more transformations. So here's some sort of exotic example. I use circles in my space, and I have some reflection that somehow maps the blue to the red circle. And maybe we'll see at the end what that is. Okay, questions so far? I can always ask questions. Otherwise, I make awkward breaks. Okay. So why should we use this? Why should you use this? These higher geometries, well, there's lots of them. Yeah? That means you have some choice. That means you can use a geometry that is suited to your problem. Yeah? Of course, first you need to figure out which one and so on, but it just gives you a sort of, I think of it as a toolbox, yeah, or I don't know, a box of toys, yeah, that you can play with. And I also want to make the point in the talk a bit, you know, take away some fear. Yeah, it's not hard to implement these geometries. So we see a bit of examples of this. But there's also sort of a warning, or it's not a quick fix. Yeah, you can't just take your problems, throw higher geometry at it, and then somehow this helps. Yeah, it involves a bit of thinking about how to solve it. Yeah, I think earlier someone said there's no, I forgot, free cake, free cheese, so it's free lunch. Still true. Okay, but it sort of enhances your powers. Yeah, if you know about these higher geometries, can use them a bit. Okay, these are gonna be, you know, strong statements, but I think to some point it doesn't help you much, and then there's some sort of frontier, and you can solve problems that others couldn't. Yeah, even you could not without. Yeah? And that's also my personal experience, both in applied and also in pure math. And something I also like, yeah, it can simply provide new solutions that are more beautiful, yeah, more elegant, maybe just improved solutions. And I'll try also to give examples of this later. Okay, and the first example that is sort of well known and in some way you've all seen is Möbius geometry, and it's inspired essentially from stereographic projection. What is that? You probably had this at some point in your undergrad or something. I have a sphere, the gray thing, and I want to project it to the plane. I use some point on the sphere, for example, the North Pole, yeah, on the top, and then you can imagine a source of light, yeah, projecting the sphere onto the plane. You know, rays of light emitting from the source, and then they give you this picture down here. And if you forgot about your undergrad, then you may Okay, you need to use some imagination now. Here's a picture of the planet Earth, yeah, from the South Pole. Can roughly imagine how it looks. Yeah, it's somehow Europe and America very small in the center. And then I wanted to ask this question: yeah, what if the globe turns? Yeah, what if I rotate my globe and still project from the same point, or you could change the point that you project from? That it looks like this. Yeah, so here's two stereographic projections that were done 400 years ago, sort of. That showed different sides of the planet, and you can see a few properties. Yeah, first of all, you see there these circles, yeah, longitudinal and lateral circles, and where they intersect. Yeah, if you pick any two where they intersect, they're still orthogonal. Yeah, that's an important property. So it's somehow nice with angles, but you also see, you know, this the most giant continent on Earth, yeah, Antarctica, somehow outsized. Yeah, so stereographic projection does not preserve area. Yeah? Right, first questions until here. Yeah. If not, okay. If not, we do a bit of formal explanation. What is Möbius geometry really? The nice thing, it's mostly just points. Yeah, so a space is just standard points, except you add one. Yeah, that's doesn't depend on the dimension. We always add one point, which we call the point at infinity, because it's sort of infinitely far away. And what do we allow as transformations? It's the standard Euclidean transformations, but we also allow these sphere inversions, or the plane, they would be called circle inversions, where we reflect about the circle. That means you need to know what that is. So here on the right, you see a black circle, and I start some blue point P, and I want to reflect it about the circle. Then I get this red point Q, and there's many ways to define it. For example, just by this distance formula, the distance of P to M times the distance of Q to M should be R squared, where R is the radius of the circle. Or if you like, old school geometry, then you can draw the two tangents and this gray line and intersect it with the connection between P and M, and you also get Q. And there are more ways. And you see this definition is symmetric. I could change the role of P and Q, so it's really an involution, which is why we call it inversion or reflection about a circle. All right, so some properties of Möbius geometry. As I said, right, lengths are not preserved, area is not preserved, not even straight lines are preserved. If you look at this example, I have a blue line and the blue straight line. I reflect them about the black circle. I suddenly get two circles. So in Möbius geometry, circles and lines play the same role. However, together circles and lines are preserved and angles are preserved, right? I've drawn this here in GeoGebra. This green angle between the line, the intersection angle of the line and the circle, will still be the same angle after the reflection. And this is why Möbius geometry is called conformal geometry. Conformal just meaning it preserves angles. And if you have some application where you care about angles, but not so much about area, then this may be the geometry for you. So in general, if you have some sort of local scaling theory, then it may be really helpful to think about this in a Möbius way. So here's some other example. Here we have sort of touching disks. Here we have a mesh of a surface touching disks. Or took this, please. No, and good question, very good question. No, in this case, the circles are still viewed as the set of points that's on them. Later this will be different, but here, we view circles as sets of points. More questions? Okay, so then we can come back to one of Felix's pictures. He had this circle pattern. We could imagine this is in a plane or in 3 space, doesn't matter. Have this quad mesh with circles. And now I can really apply a Möbius transformation to it. Points will go to points, circles will go to circles. I get a new circular mesh. Some properties that can be nice is under these transformations, the intersection angles of circles will remain. So if you want to use some cotan weights or something. And okay, now I don't have a really big picture, but you can use really big circle patterns and then sort of one interpretation, and for example, discrete conformal theory is that sort of the radius of the circles is your local scaling, because that changes when you apply Möbius transformations. Let's leave it here. Okay, now before we get to examples, I also just want to show implementation isn't hard. In the plane, we can just use complex numbers. It's late, so I have put really all the basics here. I squared is -1. Translation is just addition with some complex number. Rotation, scaling, I just multiply with the complex number. Reflecting is taking the conjugate, for example. And the new thing is the sphere inversion. It's also very simple. I just take inverse conjugate, and I can combine all of them to get a Möbius transformation. And either it's orientation preserving or not, and this is the form. And if I compose Möbius transformations, it will still be Möbius transformations, so that's very practical. And if you want, you can represent this as a matrix A, B, C, D, and composition will actually be matrix multiplication. So it's really almost trivial. If you're in space, you could use quaternions, yeah. Some people are afraid. On the other hand, when I teach the computer graphics people, they always explicitly like ask me to teach quaternions. And how do you do it? Well, quaternions are these weird numbers where the squares of I, j, and k are still -1, but ij is k and ji is somehow -k. So the numbers don't commute. That's a bit, seem annoying, but again, you can model quaternions as matrices, and then it's again straightforward. Okay, and how do we interpret this for 3 space? It's just that the I, j, and k part represent R3, the unit vectors of R3. And then we're sort of back. Translation is addition. Scale rotation is conjugation. So now I have to sort of do something from the left and right. Sphere inversion is again just inversion in terms of quaternions. Möbius transformations, sort of the same. I just have to be a bit careful because, as I said, left and right multiplication is not the same. So I really have to respect this order. Okay, and because it's sort of short on time, I'm gonna be very rough here. There's another way to do it if you prefer linear algebra, yeah, which works in all dimensions. Here's a picture I stole from a colleague of mine. That's in a book that hasn't been released, so there's no real reference here. But what you do is, if u is your point, yeah, you just represent it by 2u and then the absolute value of u squared -1 and then +1. Why should you do this? Well, for example, because it also allows us to represent spheres. Yeah? So C would be the center, R the radius of a sphere. And then we have almost the same formula. Yeah? Except now this -r² pops up. And it means we can very easily get to the intersection angle. Yeah, if you have some sort of theory where angles are important, yeah, you could also use this for circular meshes. Then this gives you very quick computational access. And of course, you can do much more with this model. Okay, before I go to examples, questions so far? You can also ask for slides back. Yeah? If not, I'm going to do first my favorite personal example. It's called canonical Möbius subdivision. What's happening here? So a lot, but what I want to focus on is, you have something in the top row and you want to get to the bottom row. Yeah, and in the top row there's some rather coarse mesh and you want to have a way to get down to the much finer mesh. Okay, that's subdivision. But this is a very special way of subdivision where you make no choices. Yeah, so that's why it's called canonical. And it respects, it's inspired by Möbius geometry and it respects Möbius geometry. So you could take a mesh reflected about a sphere, subdivide, or you subdivide first, then reflect about the sphere. And it has the same result. And from this picture, it's a bit hard to tell. So I took a second one out of the paper, which I like because it really visualizes what it does. Yeah, this 0 is my input. Yeah, so it's sort of, I don't know, a wizard's house or something. And then apply Möbius transformations, yeah, and because Möbius geometry likes spheres, the output will be more and more round until you sort of end up with the mushroom. Yeah, and so if you have, yeah, anyway, take a look at this paper. I like it. Then there's another example before someone sort of kills me. Of course, there's a long history of papers working on this. Yeah, like started Alexandrov maybe somewhere in pure math, and then there's lots of papers from all sorts of people. I wanted to start, but I picked one which I like and it's nice, and it's called this conformal equivalence of triangle meshes. What is the idea? Well, I have a mesh. I want to get the texture on there, and it should look nice. Okay, we can debate what that means. I would say in general, if things are scaled locally, that doesn't bother us so much. But if there is somehow, folds or somehow angles are not continuous, that looks really bad. And this is what they try to solve here, or what they propose a method for. And it's really strongly based on Möbius geometry. Yeah, okay. And I sort of want to, this is later paper, which I want to get to. But before we go there, we need to look at another advantage of Möbius geometry, which is these higher geometries, they usually, they're related to each other. And so in this Möbius geometry, we can find other geometries as special cases. For example, I could look at Möbius transformations that preserve some circle. Yeah? That circle has a radius, and we can distinguish cases. Yeah? For example, if here the radius squared is 0, then we're just back in the Euclidean plane or in Euclidean geometry. Yeah? So, okay, that doesn't help much because we know how to do this. But one can also fix a circle of positive radius, positive real radius. Then one can do hyperbolic geometry. Or, this is a bit weird, but one can, by complexification, fix a circle that has, imaginary radius. And then you can do spherical geometry if you want. Yeah, I don't really know an example here. But the thing is, I want to go to this example, example 3. And first I wanted to make, use this as an example of Möbius geometry, but then I looked a bit deeper into the paper and it looks very nice. Again, it's about conformal equivalence. I won't go into the details, but here's another very nice picture out of it. And, there's Euclidean, there's hyperbolic, and really it uses very strongly connection to hyperbolic geometry. Yeah, the idea is start with some mesh, find some hyperbolic structure in it, and then you can also change combinatorics while respecting some hyperbolic structure. Yeah. And it's been really key sort of in this paper to use this connection. So I hope another example that motivates a bit, that you could think about other geometries than Euclidean geometries, even if ultimately you're solving Euclidean problems. Yeah. Okay, that will be the end of Möbius geometry and almost of my time. So questions so far? Okay, if not, I'm going to have a bit more of a crash course where I present some other geometries, in much less detail. So first there's the second higher geometry called Laguerre geometry, going back to Laguerre, which is sort of the dual twin of Möbius geometry. I'll start formally. So what is the space? It's points and oriented spheres. So in this case, spheres are suddenly treated in the same manner as points. Oriented means I distinguish sort of if a sphere is oriented to the outside or the inside. Yeah, or from a manifold perspective, it could really be the orientation of the manifold. And now I allow transformations that are, again, Euclidean transformations and some Laguerre inversions, and I would love to explain them directly, but it's a bit of a mess, so it's going to be much, I feel, easier to explain when I explain how to implement Laguerre geometry, which I'll do right now. So the idea is, if I have a sphere, again, I have a center and the radius. Now, because the sphere is oriented, the radius can be positive or negative. Yeah? This is supposed to encode if the sphere is oriented to the outside or the inside. Yeah, and then I choose a representation that's quite easy. Yeah, I just write down the center, so C, and then in the extra coordinate, I write down the radius. Yeah, and the visual model you could have in your mind is this. So E is the base plane, and for example, I have this green circle there, and then I put the center of it is this yellow, the lift, CR is this yellow thing above the plane, and then I get the circle just by looking at the light cone, cone of rotation, intersecting it with my plane down here. If I oriented the circle the other way, I could just put the yellow point instead of above the plane, I could put it below the plane. And oh yeah, sorry, I took this picture from this unreleased book. One can do a few things with this. Distances, again, will not be preserved. This time angles will also not be preserved, but one can calculate tangential distances. Yeah? So the distance from green circle 1 to green circle 2 is just a distance from this point of contact to this point of contact. That's the tangential distance. And that is something that is preserved under what? Where we can model Laguerre transformations just as the isometries, pseudo-isometries of R21. It's almost like standard rotations. So if, I don't know, if you do Laguerre geometry in the plane, this will really be R21. In space, this would be R31. And if you look, I mean, we can still do these rotation matrices, except some cosines will become hyperbolic cosines, some sines will become hyperbolic sines. So it's not too hard. And yeah, what is preserved? I mean, why should we use this? Why should we care about this? Lengths and angles are not preserved. Okay, lines and tangential distances are preserved. So this is different than Möbius geometry. This time lines are preserved, which can be really helpful. And contact is preserved. So if I have two spheres that are touching, so if I go back to this picture, a second sphere that touches, or a second circle that touches the first circle would be if the yellow point of the second sphere would be on this light cone. Then you do the projection, then you will get the touching circle. Also, if you have, how do I represent lines? I don't know. For example, one of these white lines is represented by one of these other planes here. So sort of a plane that intersects the base plane with angle 45. This way you can represent lines. And so contact between lines and circles is also preserved. I feel in the plane, I'm not so sure how many applications there are, but in space this can be really useful because then you can model tangent planes and curvature spheres and so on, and you preserve contact. And also, if you care mostly about the normals, normals, tangent planes and bijection, then it's very well sort of included in this parametrization. And in Felix' talk, we had these conical nets, and that's exactly what happens. You have sort of cones. You could take any sphere in this cone. It's going to touch all the four faces. You can make this with orientation, and then you can take a conical mesh. You can apply a Laguerre transformation. You get a new conical mesh. And it's particularly suited for offset transformations. So one very easy Laguerre transformation is where you just add some number to all the radii. Then some spheres will be bigger if some spheres will become bigger if the radius is positive. Some will become smaller if the radius is negative. And okay, it's mostly used, as far as I know, in this architectural style geometry. Okay, but my time is short, so I'm not going to talk too much. There's also a more modern paper, principal symmetric meshes, and I don't know if it's on here, but if you read it, they will talk about Laguerre geometry, but they will also talk about Möbius geometry. They sort of have two stories in there for these principal symmetric meshes, which are special meshes that are symmetric with respect to the principal parametrization that we had in Felix' talk. And how does it come that they have two dual stories? That's because there's some unifying story. You can view Möbius and Laguerre geometry together. It's part of a bigger geometry called Lie geometry. I'm going to do this only very briefly. Now here in this geometry, we take points, we take oriented spheres, oriented planes, and they all make up our space of objects. And then we have a bigger isometry group. Depending on your dimension, that will be this, again, can be represented as a matrix group. If anyone finds a really good application in applied math, let me know. I'm not sure, maybe there will be, I'm not sure at the moment if there is. And another picture crashed. Oh. Okay, I don't even know what was in these pictures. Anyway, it's late, sorry. I have two math examples because, as I said, it's not applied examples. But you could apply them because it's discrete surface theory. It's about discrete meshes. The first one is a bit older, and the point was to understand, how are conical meshes and circular meshes related? Actually, they can be considered as one class of objects. And then there's a pretty new paper, still only on the archive, where we generalized this a bit, and we have these binets that Felix was also talking about, and they are very naturally invariant under this larger class of Lie transformations. Okay, so 5 more minutes. I want to not just talk about sphere geometries. There's other geometries that may be practical in other applications. One of them is Plücke-line geometry. But before we go there, something really classical. If you ever had the computer graphics, like 1 course or something, I hope you saw this matrix A. Yeah, because it describes how a computer actually renders your scene on your screen. Yeah. But it's a bit weird because it's a 4x4 matrix. Yeah, and you somehow have a 3D scene. And the reason is that they actually implicitly use, very explicitly actually using projective geometry. So what is that? The name projective geometry sort of is a tell. It's about projections. In this case, the space is all points, but I add directions. Yeah. And transformations will just be these linear transformations 1 dimension higher, which explains why on the previous slides, if I care about R3, my matrix will have 4 components, or 4x4 matrix. And of course, that's useful for everything that involves perspectives. This worked, yeah, here's also a photograph. You may have seen this building. At first, I wanted also to take the Guggenheim thing, but it doesn't really have straight lines, so it's not as instructive. But here's a projection, yeah, and if I would have had a second picture, yeah, then 2 pictures would be related by a projective transformation, which is why these projective geometry is used, for anything that involves pictures. Yeah, I don't know. In my lectures for the students, I usually do QR codes. Yeah, how do we recognize a QR code? Take some projective transformation that takes it back to standard form. That sort of motivates them to listen to me. Anyway, we still also want to cover Plücke geometry, yeah, because you could say this is a bit old school nowadays. Who does classical rendering? You all like ray tracing and so on. So that's a good hook for me because Plücke geometry, we actually talk about lines in space, and use these projective transformations from before as transformation group. And really, it's about incidences. Yeah, when do lines intersect? That's a typical problem in ray tracing. Yeah, so I copied this from Wikipedia. This under Plücke geometry, if you scroll all the way down, it would say that it's used a lot in ray tracing. Why? Well, implementation is very easy. If a line spanned by 2 points, A and B, I just represent this line as a cross product of A, B, and differences A, B. Now it has 6 components, and I can very easily check if 2 lines are intersecting. Yeah? And there's also a way to encode planes and points, so we can check for when do lines intersect planes, and so on. Okay. I don't know. What you see is a frame. Yeah, a frame. How does a frame look? It has 3 vectors that are orthogonal and normalized. There's also higher geometry for this, but it's really a bit. So it's the reason it's at the end of the talk because I don't even completely understand it. I would say it's easy to implement again with quaternions. Just need 2 different quaternions satisfying something. Then you can get your base point of your frame by Q1 times inverse of Q2, and you can get the other sort of the unit vectors also by conjugation. I wanted to use this as an example, yeah, shape from metric, because I've seen some very nice talks, and I've talked a lot with Albert about this. But it's not really an example of this frame story because in the first sentence of the abstract, they talk about isometric immersions, and that means we're not in this conformal. So this, I didn't write it, but it's a sort of conformal frame geometry. However, almost the same authors have another paper. It's just much more abstract. Yeah. And here it's not just about isometric, but also about conformal immersions. I'm not sure if it has no application or if they just thought it's too hard. But maybe in the future, maybe someone of you will find this useful. Okay, and so now just a quick recap. what we've done. There's all sorts of geometries. Yeah, I didn't list all of them. There's Euclidean, Möbius, Laguerre, Lie, Plöckel, the Studi frame thing. Euclidean is standard, of course. Möbius, I would say, is quite successfully used already. There's a lot more examples than what I've shown you. Laguerre is still a bit niche, I feel, but could maybe be used much more. Lie, maybe in the future, at the moment, mostly used just in math. Plöckers, okay, it's somehow in every rendering engine nowadays. There's more applications. StudiFrame maybe will be something in the future. Oh, I should say, okay, there are lots of applications, but they are in kinematics and like mechanics. So I don't know if it's relevant here. Okay, and if I've piqued your interest a bit, and if you actually want to see some of the missing pictures, you can look in one of these books. Yeah, so the first book is sort of one of the Bibles on discrete differential geometry by Sasha and Yuri. There's an introduction to Möbius geometry, especially if you like quaternions or Clifford algebras. There's a nice book on line geometry by Hannes and Helmut. There's a new book explaining Laguerre geometry. There's sort of a modern classic, if that makes sense, about Lie geometry. And here is a book about, okay, the universe of quadrics. Sounds very nice, and then contains information about the Studi quadric. And also, since it's the end of our joint talk, we picked a few topics, 2 topics essentially from DDG, but there's more topics that we didn't cover at all, like discrete exterior calculus or something. So I'm just adding a book that hasn't anything to do with what we talked about, but that's also nice. A nice lecture, like lecture notes from Keenan. Yeah, if you want to know even more about discrete differential geometry, you can look there. And that's it. Thank you. Any questions? All right, if not, enjoy the rest of the conference and dinner. And yeah, thank you.